Hello, this is PSYC2211 Lab 3 video titled Black Hole. As for our objective, we are supposed to create a program that generates the motion path of a star orbiting around a black hole with the arrows that show daily updated Fnet, F parallel, and F perpendicular forces based on FG, or force gravitational. Now, at the end of the day, we need to find the mass of the black hole based on the data calculated from the email seed giving the initial trajectory of the star orbiting the black hole. Now, what are we supposed to understand from this experiment? That creating and analyzing the star's change of momentum and motion allows for greater understanding of both the forces perpendicular, parallel, and centripetal, and how they affect the motion of an orbiting object, such as the object slowing down, speeding up, or remaining constant. Formulas and theories utilized with both the momentum and force degradation formulas in both perpendicular and parallel components with momentum and force parallel. Then we have the Fnet equals Fg, which is the general assumption as the only force acting upon the star is the force gravitational of the black hole. And we have the gravitational force formula, which is going to be utilized to find the mass of the black hole. Then Newton's second law, which states an object will accelerate in the direction of the net force on the object system with the summation of forces from the surroundings on the object making the net force, or the Fnet is equal to the change in momentum over change in time. Now, I will now show my model on GlowScript, which will show the motion of the star along. As you can see on GlowScript, we can see that my seed is right here. The general summation of forces to create basing on the seed versus the index and the initial points on the object, which we'll show later. Then the background, then the forces, the system properties and initial conditions, and the calculations loops shown here. And then when we run the program, we can see that the star motions around here with the force orange being the Fnet, the force green being the perpendicular force, and the force parallel being the purple force. Or arrow, sorry. Now, as you can see here, the mass is being printed over and over again to show based on the new forces and new distance given to the black hole. Then we have the Fnet, parallel, and F perpendicular right here. Now to move into the initial value. In the model of the star structure in black hole, we can solve that the initial value of the seed, the origin point of the black hole, the gravitational constant, the force of the star, and the delta T, which we measure out to be 1 days in seconds. Now, some of the values that we have found are the Fnet, which is 9.47 times 10 to the 28th newtons, F parallel as 2.353 times 10 to the 20 newtons, Fnet perpendicular, which is 9.14 times 10 to the 28 newtons, and the mass of the black hole at 1.41 times 10 to the 34th, which we as the start of the initial motion of the star. We can now analyze both the changes in momentum and force formulas from the GlowScript code in better detail with the velocity initial, velocity final, momentum initial, momentum final, finding the change of velocity, change in momentum as shown here with the final initial, then dpdt, which change of momentum over change of time is just the same thing, which is equal to Fnet, then finding the parallel direction, magnitude, and the change of momentum, change in time parallel, it being that equal to the Fnet parallel, and then parallel perpendicular is equal to the change of momentum over change of time minus dpdt parallel equal to Fnet perpendicular. Now we can also see the mass of the black hole formula right here, which I used the magnitude of the Fnet force, which is Fg, the star magnitude of the star's position, which is only the star's position is needed squared because the black hole's at the origin, so where the star's position is magnitude to the origin is the same distance to the black hole, divided by the g constant and the star's mass, and it's per every time for the while loop. Then for the error force construction, I use a scalar of 1.5 times 10 to the negative 17 for the Fnet parallel, and Fnet. Now we can go to the model analysis of mass of the black hole explanation. Now for the model analysis, the force of gravity compared to the motion of the star causes the star to slow down and speed up depending on the separation between the two resultant vectors. The angle is shorter than 90 degrees. The object will speed up with the force parallel pointing in the direction of the motion. At the 90 degrees, the speed will remain the same because there's no Fnet parallel and only Fnet perpendicular. Then at greater than 90 degrees, the object will slow down as the resultant force parallel due to the gravitational force pointing in the opposite direction. Now for finding the mass of the black hole, as explained before, we manipulated the gravitational force to utilize the gravitational force formula in order to find the unknown mass of the black hole. For the formula, since the center of the black hole is at the center of the origin, like I said before, this can be found using the magnitude position, using the change of gravitational formula distance to get to this consistent mass of the black hole, which is found to be 1.41 times 10 to the 34th. As for the improvements that we can make to be able to code it in the lab, we can see that while there isn't much to change, there can be improved manipulation of the gravitational formula to add the black hole's location to find the exact distance between the black hole and the star. We can also, for the scale of the vectors, I would next time make it slightly smaller, as for a better visualization of the vectors as shown to be kind of big right here. To answer the question as to the difference between the net force and the change of momentum, as shown here, we can find that both the change in momentum and the net force is equivalent in terms of direction and magnitude, and when you're generally excluding the change in time, but they have different meanings, as the force indicates all the force acting upon the object with the object's acceleration multiplicative to the mass of an object that is accelerating, and the change of momentum represents the change of an object's speed manipulative to the mass of the object, both containing acceleration versus velocity. Finally, we can conclude with the what if question as with what if there was a new black hole replacing the old black hole, while the star's motion would be the same, would the mass of the second black hole be different? Now, since the motion of the star for the first black hole to the second black hole is equivalent, the Fnet has to be consistent with the Fnet of the second black hole based on the Fnet perpendicular and Fnet parallel have to be consistent with both formulas in order for the motion to be consistent between the two. Now, with this in mind, we can guarantee that the distance between the black hole and the star, because since the motion is the same, the star's mass and the gravitational constant are the same, then we can conclude that the mass of the second black hole has to be not changed or the same as the first black hole, since all of these, Fg, mass 1 of the star, gravitational constant, and the distance have to be the same, therefore mass 2 is the same.